The first of the 5 types of reactions that we have is known as a synthesis reaction. Now, to synthesize means to make something. So when you look at each of these examples here, you'll see that there is one product in each of these equations. And so a characteristic of synthesis reactions is that one product is formed from 2 or more reactants. Usually you're going to see 2 reactants rather than 3 or more, although it can happen because in order for a reaction to occur, a collision must first occur. And not only do particles have to collide, they have to collide in the right orientation with sufficient energy to cause a reaction to occur. So to get 2 particles to be able to collide in the right orientation with the right amount of energy, that's enough of a challenge without requiring 3 or more particles to all collide in the right orientation with the right energy. So usually you'll see 2 reactants, but sometimes again you can have more than that. Here we have the synthesis of ammonium chloride and also the synthesis of water, taking hydrogen gas and oxygen gas, creating water. Obviously this would also involve some energy needing to go into the reaction. That's a topic for another lesson. So the general reaction, the general equation that we have for a synthesis reaction is we will either take an element plus an element, or a compound plus a compound, or we could have one of each, an element plus a compound. But regardless of what that combination of reactants is, the product will always be one single product. For a decomposition reaction, our second type, to decompose, means to break down. So in a decomposition reaction, we start with one reactant, and that reactant breaks down into simpler components, multiple products. And so what we have here, you can see the decomposition of silver oxide breaks down into its component elements, the metal and oxygen. This is a similar reaction is how oxygen was actually discovered. Mercuric oxide is how oxygen gas was discovered. Mercuric oxide is a reddish powder. When it was heated, it was seen that there was droplets of a silverish liquid, that was the mercury, condensing on the sides of the test tube, and there was also a colorless gas that was given off, and this was later proven to be oxygen. The second equation you see is for the decomposition of carbonic acid. This is what's happening inside your bottle of soda whenever you break the seal and you get that pressure release. Carbonic acid is only stable as H2CO3 under pressure, and when you release that pressure, this decomposition reaction begins to proceed on its own. So the CO2, the carbon dioxide gas that's generated, that is responsible for your bubbles, and so when you leave a soda open, it tends to go flat, and not only does it not have that effervescence, that fizziness anymore, but it also tastes kind of watered down. And that's because literally you are diluting the syrup and the flavorings even more because water is being generated through this decomposition reaction, and it's serving the effect of diluting the other materials that are dissolved in that solution that makes up the soda. The last decomposition equation you see here is for hydrogen peroxide. Whenever you put peroxide on a cut and you see that it fizzes, this is the reaction that's occurring. The iron that's in your blood is actually helping to speed up or catalyze that reaction and cause it to go faster. There are other catalysts that we can use to speed up this reaction, such as in the popular demo elephant toothpaste. The general reaction then for a decomposition reaction is that we will always start with one compound. What we get from that compound depends on exactly what that compound is. We could get 2 smaller compounds, we could get the 2 elements that might make it up if it's a binary compound, or we could get a combination of each, and you see examples of these in the 3 equations provided. The next type of reaction are sometimes referred to as replacement reactions or displacement reactions, and they come in 2 varieties, single and double displacement. In a single displacement reaction, what you have is a free element and a compound that serve as your reactants. Your products are also a free element and a compound, but you'll notice that they are new element and compound compared to what was started with. And the best way well, I don't know if it's the best way, but a way that I would describe it is when you're at a dance and you've got somebody that came by themselves and they'd like to dance with somebody that's already on the dance floor. So they might go out and ask if they can cut in. And just as in that situation, sometimes the cutter-inner is successful and able to then dance, sometimes they're not, and nothing happens, nothing changes. Such is the case also with single displacement reactions. Now when we look at these examples, how do you know which element the free element is going to try and displace? We need to ask yourself, what kind of element is it, and what kind of charge would it typically take on? So in the first case here, chlorine's a nonmetal. Nonmetals like to gain electrons, so when it comes up to the potassium bromide, so to speak, it's going to try and displace the bromine, because in the case of ionic compounds, opposites attract. If chlorine's a nonmetal, wants to gain electrons, has a negative charge, it's going to be attracted to the positive potassium ion. So chlorine will try and displace the bromine, and if it's successful, then we would see the products formed, potassium chloride and bromine. If it's not successful, then nothing happens, and you still have the original chlorine and the potassium bromide. Likewise, in the second example with lithium and curium fluoride, lithium is a metal, tends to have a positive charge, so it's going to target for displacement the curium and curium fluoride. In the last example, you have a classic reaction of an alkali metal with water to produce hydrogen gas and a base. So your alkali metals are very active metals and typically are very much able to displace any element that they are trying to replace out of a compound. So the general formula that we look for is element plus compound yields another element plus another compound. The exact order in which they appear in the equation does not matter so long as you have one of each on both sides. Depending on what the free element is, we can classify single displacement reactions as cationic single displacement. That would be whenever you have a metal that is trying to do the displacing, that is the free element to start. So the second and third equations on the screen here would be examples of cationic single displacement. Anionic single displacement would be when you have a non-metal that is trying to do the displacing, such as the first example with the chlorine. The second type of replacement or displacement reaction is known as a double displacement reaction. And think of the same analogy going to the dance, except now you've got two different couples that are dancing. And at some point they decide to switch partners. So in the first example here you have lead originally dancing, if you will, with chlorine for lead 2 chloride. And then you have lithium dancing with sulfate for lithium sulfate. At some point they switch partners. The lead goes with the sulfate and the lithium goes with the chlorine. And so essentially you're just taking your cations, you're swapping them, and then obviously you need to pay attention to the oxidation numbers, the charges, make sure you have a properly written formula. Now these reactions are typically in solution. The reactants that you have, the formulas that you have, are generally aqueous, and so they will be dissolved in water, and you may not see anything. You know, you're mixing two clear liquids together. So the question becomes then, well, how do you know that something is actually generated? If we're starting with materials that are dissolved in solution and we can't actually see those substances, how do we know that they've actually made something new? Where's the evidence of that? And the evidence of it usually comes in the manner of one of three forms. One, a gas is generated, so you'll see bubbles forming. Two, you'll see a precipitate form. If one of the products that is formed from the double displacement is insoluble in water, it will precipitate, and you will see that precipitate come out of solution, either falling to the bottom very quickly, or your solution becomes cloudy, indicating that your particle size is very small, but it is definitely solidifying, precipitating, and blocking the light that would be passing through it otherwise. The third one can be a bit tougher to identify, and that is if water is produced. Typically we see this in an acid-base type reaction, which is a type of double displacement reaction, but water being clear and colorless itself, again, would be difficult to detect that visually. There are some chemical tests that you can use, some test strips that you could use to test for the presence of water. But again, that one is probably the most subtle of the three. The formation of a gas and a precipitate are the most visually definitive signs that a double displacement reaction definitely has occurred. And so as far as our general equation goes, we look for 2 compounds to start and 2 compounds in the end. So for these first 4 types, how do you classify these reactions? What you would want to do is, in your skeleton or your balanced equation that you are given and asked to classify, go formula by formula and ask yourself, what do you have, an element or a compound? And once you have classified each of the individual components of the reaction, then step back and look at the pattern and see which of these general formulas does it match. Does it match that of a synthesis reaction, decomposition, single displacement, or a double displacement reaction? The 5th type is kind of on its own, and sometimes it gets its whole own discussion, but we mention it here as a 5th type of reaction. That is a combustion reaction, when something burns. If you recall, in order for something to burn, it requires oxygen. So that is the key characteristic that you note in all 3 of these examples. O2, oxygen, elemental oxygen, is a reactant in all of them, and it must be in order for the reaction to be classified as combustion. The other characteristic, if you look at all the products, you'll note that they are all oxides. They all contain oxygen as the second element. And so if we think of the general reaction, we could either be burning or combusting a compound or an element, but you will always have O2 as a reactant, and your product or products, depending on what your fuel source is, the compound or the element, will be 1 or more oxide compounds. So you want to look for O2 as a reactant and oxygen in every one of the products. If you see that, that is going to suggest to you very strongly that you have a combustion reaction. Now, if you look at the second example here, if you have just just an element plus oxygen, and you're producing 1 product, if you recall, that one would also match the description of a synthesis reaction. So in some cases, you may be able to classify a reaction as multiple types. It just depends on the specific example that you might be looking at.